Laboratory session number 2 has to do with the deflections and stresses in a cantilever beam. I've taken a beam and put 2 concentrated loads on it and then asked the question, which way will the tip deflect? The beam has been sized to be about that of a diving board found at a swimming pool. It also vaguely resembles a fighter in that the first natural frequency is close to that of conventional fighter aircraft. Let's look at our cantilever beam with the loads on it. Here we have a downward load of 5,000 newtons and an upward load of 2,000 newtons. We know that there's some leverage, you might say, for the outboard load, but it's much smaller. So finally deciding whether to predict that the tip will move up or down seems to be a close call. Because our loads are concentrated, if we put nodes under each of these load application points, then each of the elements involved is only loaded at its ends, and we know that the cubic shape function that's used should be exact then under that situation. So our answers should be exact except for round-off error. Over here is a magnified view of the cross-section of the beam. It's 150 millimeters by 100, and I made it that way so that when it deflects it would have principal axes lined up with the horizontal and vertical, and that you'd have some sense that it would be more flexible in the vertical direction. We will choose XZ coordinates to describe this problem, and we'll only be interested in the bending in that plane. Let's consider the physical modeling that we have to do. The beam is slender, it's 3 meters long and only 100 millimeters high, so that the length to height ratio is 30. And that's quite adequate for conventional simple Euler-Bernoulli beam theory. We're not going to include shear flexibility because of that choice. The principal planes of inertia are clear, the XY and XZ planes. Since the loads are only in the XZ plane, I only am interested in the flexure in the XZ plane. So we won't consider axial extension, nor torsion, nor bending out of the plane. And why don't you guess now what you think about the tip of the beam? Will it move up or down? Next, we look at the finite element modeling. We've decided to use Euler-Bernoulli beam theory, so we'll use 2-noded Euler-Bernoulli beam elements. In the Nastran series, these are called bar elements. In Mark usage, it's element 5 or element 52. There's several beam elements. We only need to use 3 elements to get an exact answer because the cubic shape function is sufficient to exactly model end loading on a beam element. You see, it wouldn't be exact if there were interior distributed loads between the nodes. Now, the element coordinates are certainly code dependent. I'm going to concentrate on the Nastran family of codes in our current discussion. The axis of the beam is conveniently described by 2 nodes, a grid point at the A end and the B end. Then one is asked to lay out a vector V such that a plane can be described passing through the axis of the beam and then the vector V, which creates this plane number 1, which is the red crosshatched plane. Now, normally when you're setting up your element, the element doesn't yet have its own element coordinate systems. Therefore, you're relying on basic coordinates, in other words, a remote set of coordinates for the setting up of this V vector. So generally, the components of this vector are in the underlying coordinate system for your problem. Now, those are called basic coordinates in the Nastran family. Then it's not too hard to construct your Y coordinate at the element level as being lying in that plane and perpendicular to the axis of the beam, and to construct a Z coordinate direction perpendicular to this first plane we've created. Some people feel that the beam element is actually the most difficult of all the finite element family of elements. And this is because you have to orient the principal directions for the inertial reference. And I know that I myself have goofed this once on a problem where I got the rectangular cross-section referred in the opposite manner. So it's not a trivial thing, and especially when you have beams that are inclined at angles to the basic coordinates, then you have to watch it. But element by element, it's actually a clear procedure depending on the code you're using. Here, for instance, we show the final result then of establishing a plane 1 and a plane 2 for this particular beam element. Let me remind you that the so-called axis of the beam for a simple Euler-Bernoulli compact closed cross-section is the centroidal area. But as you move to thin-walled open cross-sections, such as channels and Z-shapes and so on, then the most relevant axis to describe your element by is the line of shear centers. And so it's really the shear centers that we're concentrating our attention here. Or some people might call it a center of twist. In any event, this set of planes is laid out at the left end of the element as we've numbered it here. In our particular problem now, this is problem dependent, we're going to constrain the degrees of freedom at the wall so that all 6 coordinates are fixed. Then in the remaining portion of the beam, to constrain it to lie in flexural motion in the XZ plane, we'll constrain the axial motion and the deflections out of the plane, the torsional or the twisting of the beam, and then the rotations that would carry the beam out of that plane, which would be about the Z-axis. This effectively brings you into a restricted two-dimensional space for flexure only. For column action, you'd have to release the degree of freedom number 1 to let the beam, in order to get a beam column, to let it expand and contract axially. Now our loads are going to be under nodes 2 and 3. We've got the 5,000 Newton load downward, the 2,000 upward. The sign convention for beam theory is very important, and there's a natural conflict between the classical sign convention for force resultants from the finite element sign convention. Here I show the finite element convention with the red components of force and moment, both at the left and the right ends. Then the classical theory is shown in blue in the center. Now, the reason the finite element theory is easy is because both the shearing force and the bending moments are positive in the positive coordinate directions. And you use the right-hand rule to interpret this double-headed moment vector. Now, that same convention holds at the right end of the beam and at any other node in the entire structural model. But the interior force resultants are described in a different way classically. A common convention is that a positive moment will cause compression in the positive fiber of the beam. For instance, if we look in the XY plane here, then the moment that would tend to cause bending in that plane we'll call M1, and if we make it positive upwards, then it will curve the body, as you can imagine, in this direction, such that the top fibers, those that are farther in the plus Y direction, will be in compression, and then the bottom fibers in tension. Then when you do the same thing in the XZ plane, you find that the positive moment defined on this positive face of the element moves to the left. And so that one is counterintuitive and doesn't agree then with the coordinate direction plus y, but rather lies in the minus y direction. Now it's the moment M2 that will lead to flexure in the XZ plane, and it would be this moment we'll look at in our own solution later. There also are sign conventions on stresses. Here I show the body, again, a single beam element with ends A and B, and you show that the force at the left end would be such as this F sub x in the positive coordinate direction, positive x direction, likewise on the right end. But stress in a classical theory is positive when it's in tension. So you get, at least on the back face here, you get the positive stresses acting in the negative x direction, and that's okay. So blue is classical and red is finite element. Now to recover stresses across the cross-section, the finite element codes ask the user to identify points of interest. On a rectangular bar like this, you could have picked either top and bottom mid-side points or corners. Since there's no torsion in the problem, there really is little distinction about what's happening at those extreme fibers. And of course, in our bending situation, we'll be interested in what goes on at this top surface here as opposed to the bottom surface here. Let's consider the MSC Nastran data for this problem. Of course, we have our 3 bar element problem here where the 3 simple Euler-Bernoulli elements have been chosen. The first thing that we need is a file management statement, and in this case I'll post-process with the post-processor ideas, and this is the general statement used along with a parameter card, param, comma, post, comma, -2 for ideas. I found in the latest release of ideas, however, that they like to use the extension OP2 for output 2. They don't use tick marks, and they often will follow, for creation of a new database, the file name is followed with comma new, comma. So check out your own installation. In any event, it's wise to think a minute about the file management and how you get your graphical data out of Nastran. Okay, the executive control statements are rather easy because we're using the static solver and we put in a 1-minute time estimate here. My Hewlett-Packard machine, a Hewlett-Packard 700 computer, solves these problems in just a couple seconds, so it's not much time, and this time estimate is in minutes. Case control has the conventional requests for echoing out some of the data, some, all, or sorted data. We're going to echo out the alphabetically sorted data. Then we're going to want all of the displacements that we've calculated. Of course, we also want all the stress and force-like things to be read out. So we do ask for all stresses, element forces, and SPC forces, which are, of course, the reaction forces. We have only one subcase with a given load of 5,000 newtons down at one point and 2,000 up at another point. Bulk data, we ask for the auto SPC feature in case we have an error at the grid point level. We do ask for ideas output. We're going to use the grid set card to constrain this body to move in the XZ plane, and these constraints convert the problem into just that, flexure in the XZ plane. It's in the 8th field. Our grid cards are pretty easy. Our point at the wall, and then the subsequent grids that are out at 1,000, 2,000, and 3,000 millimeters from the wall. At the wall, we will constrain all 6 degrees of freedom, and then the default on the grid set will act in all the remaining grid points where the field number 8 is blank. Connectivities are rather straightforward for a bar element. For instance, our first bar element, number 1, only has to connect grid points 1 and 2. Then we call out a vector v with components in the basic coordinate system of unity in the x direction and unity in the y direction. and that establishes plane 1 for the local element coordinate system. Then the C-bar card refers to a property card below. That in turn refers to a material card, so we get that triple whammy of 3 in a row. The property card is actually rather intricate because we have to call out the cross-sectional area in millimeters squared. Here's the moment of inertia I1, which tends to oppose flexure in the 1 plane. I2 is what we're interested in. It opposes flexure in the 2 plane. Then there's some fields that we're not interested in, including torsional stiffness. This card is continued and then gives paired coordinates on the cross-section that are the YZ coordinates of the corners of the rectangular cross-section. The material card will put the steel properties here with Young's modulus. We don't enter the shear modulus, and then we do put in Poisson's ratio. Our load case 50 is called out finally, and this is one force on node 2, which is minus 5,000 newtons in the z direction. It's given in basic coordinates with a scale factor of 1, and that way you can change the 3 components later if necessary by changing the single scale factor. The final force is on node 3, and it's 2,000 newtons upward in the z direction. We then use the N data card to close out our data set. Let's look at the MSC Nastran results. First of all, we find that the displacement at the tip of the beam is positive. And furthermore, it's small enough to be within the linear beam theory, so our Euler-Bernoulli theory is not violated. Secondly, curiosity occurs, namely that there's zero deflection at the second node. And that's just due to a fortuitous coincidence of lengths and load sizes that were taken as round numbers that happen to cause an exactly zero deflection there. We can also look at the forces of constraint, which would be at the wall, and you find the shear there is the proper amount and in the proper direction, as is the bending moment at the wall. We'll show these later in the shear and moment diagrams that show from classical theory what these values should be. Now we'll look at the forces and the stresses in the beam cross-section. Starting with the forces in the bar elements. Now these are the traditional classical moment and shears, and they can be used to draw a shear and moment diagram, which I'll do a little bit later for all of our 3 computer solutions simultaneously. But notice, for instance, that when you go in element number 1 at the right end, then here you see the moment is continuously carried to the left end of element 2. So we have moment continuity. Then the shears are given over here within the elements. Stresses are called out at those 4 cross sections. If you look at the sense of the moment at the wall, you see it will cause tension in the top fiber, and that is what happens. Our stress point 1 is on the upper right cross section of the beam cross section as you look at it from the end view, and then this is the upper left. So we get tension at the wall in the upper fibers there. So I'll also show these stresses later in a table. For the mark solution of this same beam problem, we'll use their element number 5. This is to be used here as an elastic element in 2 dimensions. The element is a 2-noded element, and we'll consider 3 points along the cross section. In other words, it'll integrate at 3 points through the thickness of the element. Now there are a number of commands that have to do with data printout. For the post-processing, you can call for the various kinds of stresses that you're interested in. Here we're interested in some nodal quantities, so we're asking to print for the various nodes, incidentally nodes 1 to 4, the reaction forces, the total displacements, and the loads. And there's only one such set of these items to be considered. Then next we have a element information to be printed out at the nodes, and that cluster continues on to the next figure. Unfortunately, I broke it right there, but we're going to print one set of quantities mentioned on the next figure. We'll continue that section of data by asking for stresses at certain points. Here's the stress request to be found on elements 1 through 3, which is the entire set of elements. We're only asking for stresses at the internal node number 1, which is the left end of each beam. In retrospect, I'd probably ask for both if I did that again, because you can have a jump in shear, which could affect the shear stresses. And then we're going to ask for stresses at all 3 layers of the element. Then we put on the loads on the system where we're going to have 2 concentrated or point loads given. For the grid point number 2, we're going to give a 0 x component in this local coordinate system and a minus 5,000 newtons in the y. You see, this is a two-dimensional problem and a two-dimensional element built into the xy plane in the mark special set of coordinates. Then at the third grid we put in 0x, which is axial, and 2,000 newtons upward, which is their y direction. We're going to put on boundary conditions on displacement. Next, there will be one set. So now we call out the clamp boundary at the wall, and in our coordinate system where the beam meets the wall, we have to restrain the x direction, the y direction, and the rotation, which in a right-handed system would be in this sense. So these are the 0 values we're going to impose on coordinate directions 1, 2, and 3 at grid point number 1. Connectivity, we have 3 elements. Element number 1 is a type 5 element. This element is defined with a rectangular cross-section, so later we'll put the geometric information of height and area in. This element connects grids 1 and 2, and then sequentially the next one, 2 and 3, and then grids 3 and 4. So it's easy to connect our elements. Then the nodes are defined here under coordinates. We're going to have our grid points 1, 2, 3, and 4 spaced at 1,000 millimeters along the x-axis and 0 values on the y-axis. Now we'll do our material properties. We just want an elastic isotropic material. We have one such material to define. We'll give it an identification number of 12, which we really don't use in this problem. You would later refer to that for various exotic properties which we don't use. And then we put in Young's modulus and Poisson's ratio for steel, and this material property will hold for elements 1 to 3. The geometry now, there will be 3 elements. They will each have height of 100 millimeters and cross-sectional area of 15,000 millimeters squared. And so that's true for our first element, second element, and our third element. And that's the end of the input data for the MARC solution. Let's quickly look at the MARC results, since they're essentially exact also as were the MSC Nastran results. The displacement field here shows the beam passing through the 0 point in lateral deflection at the second node, and again gives 1.03 millimeters deflection laterally at the tip and in the positive direction. So the outboard load 1. The live loads are echoed here, and we have these two concentrated loads in what is the y direction in this problem. We have x, y, and then we have a moment, and in our case we applied only y direction loads, which are vertical in our physical problem. MARC has been asked to read out the reaction forces, and we again get the 3,000 newtons of shear at the wall and the 1 million Newton millimeters of positive moment there. And then stresses come out as shown. We're only printing out stresses at the left node of each of the elements, and we get the values of 4 megapascals at the various corners of the base of the wall there where the clamp is. We'll continue with the stresses in the second and the third elements. And here we see that in element 2 at the left node we get 8 megapascals at the upper and lower fibers. The outboard element, number 3, is actually unloaded because there are no live loads outboard of that, and so you get these 0 values showing up. So it's completely unstressed. Let's look at the Astros data for our cantilever beam problem. The control cards are shown here. We're going to do a static solution. We have a title for the problem, and we're going to want out all the displacements, stresses, forces, and single point constraint forces. Let's look at the bulk data for Astros. We'll use a grid set card, and this will convert the problem into a two-dimensional flexure problem by constraining degrees of freedom 1, 2, 4, and 6, and that will be applied wherever the eighth field is blank. At the wall, however, on grid 1 we're going to constrain all 6 degrees of freedom. So that's our first coordinate. Our second, third, and fourth coordinates are spaced every 1,000 millimeters down the length of the axis of the beam. Then the elements, the bar elements, are given in order. The first element with property card 29, which points down here, joins nodes 1 and 2, and has a vector defining the 1 plane. That vector has a unit value in the x direction, a unit value in the y direction, defined to be in basic coordinates. Bars 2 and 3 follow likewise. Then the property card points to the material card 12 down below. It lists the area of the cross-section. I1 is a moment of inertia that opposes flexure in the 1 plane. I2 is a moment of inertia we're interested in. It opposes flexure in the 2 plane. And then we continue on to the next card so that we can give these paired coordinates that define the 4 points at the extreme corners where we want stress output. So these march off across the page here. On the material card we have the Young's modulus and Poisson's ratio. We don't give the G value that could have been given there. Normally, you only give 2 of the 3 material properties because a third can be calculated uniquely from those 2. Force cards, we had a load case mentioned above, and then we have loads applied to nodes 2 and 3 in the basic coordinate system, scale factors of unity, and no components in x and y, but minus 5,000 in the z and 2,000 newtons in the z direction, followed by the end of our data. Astros results that we'll discuss include the stresses, the displacements, and then internal force resultants. The displacements are shown here and compare with the other codes that we've studied. Again, we get near 0 at the second node, which is fortuitous, and then we get the 1.03 millimeter tip deflection, well within the linear theory. Stresses below here are at the wall. On the upper points we have 4 megapascals. It's a rather low stress, a rather lightly loaded beam, it turns out. And that sign means that it's tension on the upper fiber of the beam. When we go to the right end of the beam, we get -8 on the upper fiber, which is compression. That would be due to the way that the outboard load is pushing upward and the inboard load is pushing down at that point, so we're curving the beam in a way to give compression there on the top fiber. We should be able to check the moment at grid point number 2 and see that we have a positive moment there. Now let's check and see if we did get that positive moment. At element number 2 at the left end, we find there's 2 million Newton millimeters at the left end, and so therefore that is a positive moment under the maximum load of 5,000 newtons. We'll gather these results and put them in a table next. We've made 3 separate finite element runs for the deflection of the beam using 3 different commercial codes. Let's gather our results now and compare them for the different codes. We'll start out with the deflected shape of the beam. Here I've taken the MSC Nastran output and processed it by ideas. We see that the beam is represented with straight line segments, and that's quite common with the post-processors because they deal with the displacement information at the nodes, but they don't use the slope information. It's generally assumed that the mesh would be fine enough so that the angular errors would be resolved just by many small displacement points. Now all 3 codes give good results on that 0 deflection at the first node, and theoretically it is identically 0. At the tip we see the 3 codes give 1.03 millimeters of deflection, and so they agree there also. And this is well within the linear theory. Shear and moment diagrams are one of the most important features of beam theory. You've all seen these in your strength of materials courses. It's probably easier to construct the shear diagram first and proceeding from the outboard tip of such a cantilever beam. There's 0 shear in the outboard element, but then you cross the 2,000 Newton upward load, which is a positive shear in the classical sense. So the shear jumps up in the second element to this value of 2,000 newtons. Then you reach the downward 5,000 Newton load, which subtracts and causes a net minus 3,000 newtons of shear in the inner element. Moment can be interpreted as the integral of shear, so that as you're moving from the tip inboard, you can see how At this point, at the right end of the center element, you start getting a positive moment. It reaches a peak value right at the second node in the problem and then drops to this negative value. The shear diagram is a little tougher to construct, and you need to make small free body diagrams to do that. All of the finite element codes and the classical theory are in agreement, and the only difference would be a tiny amount of round-off error. The computer programs have given us the stresses in the cross-section at the 4 vertices of the rectangle. These constitute the extreme fiber positions, and at the root of the beam, where these numbers are developed, we get plus 4 megapascals at the top fiber, minus 4 at the bottom fibers. You can check that pretty easily with classical beam theory. The formula is sigma x is minus mz over I2. For the top fiber, we have plus 50 millimeters as the relevant distance, and we get 4 newtons per millimeter squared, or megapascals. The bottom fiber, we get the minus 4 because of the negative distance to the extreme fiber. In the general theory of beams, there are many special topics that arise. For instance, you can have open, thin-walled cross-sections that distort badly. We'll consider these topics here: the offset of a beam from a plate-like structure, which is often useful, the neutral axis, the shear center, the center of mass on a cross-section due to additional non-structural mass, and then the taper of a beam element. The notation here is shown from MSC Nastran, but other codes would have similar situations. First of all, if you identify a reference set of nodes, such as GA and GB, then you might want to use a plate beam stiffener combination where the beam is offset. And you'd like to refer some characteristic point on the beam to the plate nodes without creating new nodes for the beam. Now, this can be done with this offset distance at the left and the right, which is really a vector in space. You might wonder, why is the shear center taken as the reference position? And it turns out that's the most crucial axis of the beam, because it's at that point that the bending and the torsional effects in the beam uncouple. And in general, the neutral axis, which is the centroidal axis of a straight beam, is offset from that shear center. Beside that, you might have a non-structural mass acting on that beam. For instance, in the traffic transport trailer that I studied earlier as a case study, there were ladders and hydraulic pumps and such devices that weren't really centered on the beam. Now, in that case, the difference was negligible because of the total size of the system. But you might run into an application where that non-structural mass should be carried on some appropriate axis. Finally, you can have taper of the beam, and some elements, such as the MSC Nastran beam element, will allow sections along the beam to have different cross-sectional properties, and then those can be read in the data set. The end release concept is also very important for beams, and this applies to all types of beams. What you might have is a pin joint or some kind of a slot at the end of a beam which will relieve the moment or shear forces present there. I've drawn 2 examples at the 2 ends of this beam, and presumably the beam is long and slender, and I've not drawn the intermediate portion, such that these end fixtures are only a very small part of the total beam structure. I've drawn a curious fixture at the left end in which certainly the pin acts to relieve the moment about the y-axis. If I create a system of coordinates here, x, y, and z. And the cards that describe this beam are often set up with a end release field. Here's the end release field for the left end, here's the end release field for the right end. Now, rotation about the y-axis would be the 5 coordinate. Then there could be also a differential rotation about the z-axis here, just by the different ends of this pin sliding in the slot, and that would release degree of freedom 6. Then there's certainly translation along the x direction, which is degree of freedom 1. And then lastly, because the joint is kind of sloppy, it could translate in the y direction, degree of freedom 2. And so the only restrained degrees of freedom then are the vertical displacement, which is z, which is 3, and then rotation about the x-axis, which is 4. At the right end, we have a little different situation where the release allows x translation, which I show here, and then also releases rotation about the x-axis, degree of freedom 4. The simple theory that we've discussed, which is the Euler-Bernoulli theory, is very good for compact cross-sections. But when you go to thin-walled beams, then you can have some analysis problems. One reason is that the cross-section itself can change shape. It can warp and go out of plane, and then within the plane it can deform greatly. This is worse for the open-walled sections than the closed. I'll refer you to classical textbooks on this. Typical courses that are given around the senior level in mechanical engineering, civil, and aerospace departments often will have considerations of thin-walled beams. I can give an example for the problems you get in the closed sections. I used to test the thin-walled beams used in vehicles, automotive primarily, and I bent these beams about an axis shown here, and then I twisted them as shown here. Nature is perverse in the sense that these thin-walled beams, as they're loaded, will tend to cripple at a cross-sectional location. And what happens is that the walls of the body will move toward the neutral axis in a way to minimize the moment of inertia. So it's sort of a self-destructive behavior. And this particular cross-section shown here will become even more extreme until the body actually does fold at that point. That can be triggered elastically, but ultimately progresses to a complete plastic hinge. In torsion, it's even more bizarre in that if you twist such a closed-wall tube, that all 4 walls will tend to go toward the centroidal axis here, and collapsing in will give this less and less stiffness in a torsional sense. And again, you get a torsional hinge, and this will wrap up just like taffy, especially with mild steel. So beware of trying to apply the Euler-Bernoulli theory too broadly, especially when you have thin-walled beams.